Yeah. So it's my great pleasure, yes, to be here, yes, to introduce my research work on quantum software engineering. So today I would like to give a talk about quantum software engineering and sorry, quantum software engineering, landscape and horizon. So actually, yes, I'm now working uh, at Kyushu University, Japan. So before that, I have been working for Shanghai Jiao University for about 10 years. So Mohammed, yes, have visitors. Yeah, I'm very enjoying that. So, so the outline of my talk today is first I will briefly introduce background information on quantum computing, and also I uh, give a brief introduction of quantum software engineering, which includes definition and also several considerations. And after that, I will give a very brief comprehensive survey of quantum software engineering because there is a lot of work here. So I don't think I have enough time, yes, to introduce it one by one. And finally, uh, uh, I'd like to discuss some challenges and opportunity in the area of quantum software engineering. So as we know, quantum computing will impact our society. For example, so it can speed up, for example, optimization, encryption, and machine learning. And also, it can be benefit to the, for example, nature science, for example, the physics, chemistry, material, and yes, and also a lot of places, material science and something. And also, quantum computing is related reality. As you may know, that there is quite a lot companies that are aimed to construct real commercial quantum computing. For example, a company from D-Wave and IBM, Google, and USTC is the University of Science and Technology of China. They also have a very big group uh, for quantum computing hardware and software and something. So what can we do with the quantum computer? So there is a picture. So here you say, and the people say that how's your quantum computer prototype coming along? Oh, great, yes. The project exists in a simultaneous state of being both totally successful and not even started. So you have two states, totally successful and not even started. Can I observe it? That's a tricky question. So as you know, the quantum state, you cannot observe the quantum state. If you want to measure it, you want to interfere with it, so it will cooperate, it will back to the classical state, 0 or 1. So there is some special features for quantum computer. So quantum computing isn't the answer to everything, but it will almost certainly free us to solve more problems. So I think, it don't want to take over the classical computing. But by using quantum computer, so you can solve some problems that have, cannot be solved by the classical computer system. So why build a quantum computer? So as you know, quantum computer powered scales exponentially with qubits. For example, n bit can exactly simulate log n qubits. So generally, 1 qubit is more power than the classical one classical bit here. So for example, this is some quantum units. For example, Commodore 64 AWM4 instance, and also entirely global cloud computer systems. So this is by using this computer, you can simulate 10 qubits. And for example, if you use the entire global cloud computer system now, so you can just simulate 16 qubits. So size of today's system, yes, not perfect, but it shows that the quantum computing may much more power than the classical computing. So there is so by using quantum computers, so you can solve many problems in many areas. For example, in the machine learning and supply chain optimization, and also robotic manufacturing, computational material science, and also alternative energy research. There is a lot of area that will be potentially benefit by the quantum computing. So what isn't on here is breaking RAS. You know, RAS is a protocol, a security protocol. So if you have quantum computing, so you can use the shares algorithm to break the RAS. It's quite simple with a very short time. But now you almost cannot break in the RAS use classical computing system. So this picture shows that quantum hardware development is accelerating because so say that so if you see this from the 1926 that when the quantum theory appeared, and the first quantum computer is manufactured in 1982, and in 2000 there is a 7-qubit quantum computer, and in 2006 there is 12-qubit quantum computer, and now for example in 1918 there is for example there is a lot of quantum computer manufactured constructed by different companies, but now the qubit I think is doubled from the 128. So just 1 year, I think. So this is Google has as you know, Google has reached quantum supremacy in 2019, and also from China. From the University of Science and Technology of China, also reached the quantum computational advantage last year. So the other question is why program a quantum computer? So quantum computer, because quantum computing rearranges the relation between physics and computer science. So as Turing said, every function which would naturally be regarded as compatible can be computed by the universal Turing machine. And also, Feynman said that nature isn't classical, but maybe it's a quantum. So physical phenomenon applying to information computation as well. So quantum mechanism, there is some specific features in the quantum mechanism. For example, the superposition, no cloning, and teleportation. So based on this special feature, so researchers now are trying to construct a general commercial quantum computer system. So usually this is the full quantum computing system, which includes two parts. The first part is classical control racks. So there is some classical computer, and the second part is quantum computing, which we usually call a quantum processor. So between the quantum part and the classical part, there is some relations. For example, you can send a core to the quantum computer, and to make them to perform computation for some specific problem that can not be solved by the classical computer. After they get the result, so you can send back to the classical computer, so to continue work. So this is actually the architecture of quantum computer system. One type of architecture of quantum computer system. So from this picture, so you can say there is a quantum computer layer and also classical computer layer. The classical computer is just the traditional computer system. But for the quantum computer layer, so there is some parts related to the quantum computing, and especially, for example, the quantum logic gate and quantum classical computational interface, which build the relationship between the quantum part and classical part. So this is a CPU for the classical computing and the QPU for the, for example, quantum computer. So you can send some instructions to the QPU, and then the QPU compute. The result will be returned to the classical computer. So quantum programming is prepare and sampling from complete distributions. So this is actually the compare of the classical bit, probabilistic bits, and the quantum bits, qubits. So we all know the classical bit is must be either 0 or 1. But for quantum qubit, the state in the quantum qubits will be represented by this formula. So it's a combined of the 0 and 1. And alpha and beta is satisfying this equivalence. So this is a quantum programming, quantum computer program language frameworks. From this framework, you can say that in the bottom there is a quantum devices, and up to that there is some quantum machine instruction language, and quantum machine assembly language, and after that this is a high-level quantum program language, and also program system, which includes compiler system and also some optimizer algorithm optimizer. And after that there should be some interfaces to some applications. So for the quantum computing program language, usually consists this part: hardware, assembly language, quantum circuits, quantum algorithm, and then full stack library, and the quantum university languages. So it's quite similar to the classical computing program language. But in detail, there is a big difference because they are based on different physical mechanism. So based on this, we think it's a high time to focus our attention on engineering quantum software system to reap the benefit of quantum technology. So as we know, without the quantum software, you cannot show the power of quantum hardware. So because the recent various application domain of quantum computing urgently need quantum software engineering methodologies and techniques to solve their specific problems. And we think there is urgent need to build a community for quantum software engineering. For example, similar to the classical software engineering, so we need method, tools, and processes for efficiently develop a quantum software system. So next, I will give a brief introduction of quantum software system, quantum software engineering. So which includes the definition, a roadmap of quantum software engineering, quantum software engineering method, tools, and processes, and also, if I have time, I will give a brief introduce about generic view of quantum software, which is similar to classical software engineering. And also a very simple quantum software life cycle that we use to classify the papers in the area of quantum software engineering for our survey paper. So in order to give a survey in the quantum software engineering, we first give a very simple definition for the quantum software engineering, which borrows some idea from the classical software engineering. So we see the quantum software engineering, the use of sound engineering principle for the development, operation, and maintenance of quantum software that is reliable and works efficient on quantum computing. Here we would like to highlight three aspects. First, it's need a sound engineering principle for development, operation, and maintenance of software, quantum software. And such software should be reliable and also should work efficiently on quantum computing or quantum machines. So this is actually a very simple definition, but I think there will be some more precise or more meaningful definition for that. So next, I will give a brief introduction of a roadmap of quantum software engineering. So we see that the original of the term quantum software engineering is called by John Clark and Susan Stepney, which from the Department of Computing of York University, the UK. So in 2002, there is a workshop on Grand Challenge for Computing Research organized by Tony Hall and Michael Atkinson. So in the United Kingdom. So in here, there is a proposal for Grand Challenger for there is a proposal of Grand Challenger for Computing Research, which called quantum software engineering. So in this proposal, they briefly discussed some challenging opportunity that the quantum software development will face. So although they give not, they haven't given some detailed idea of how to do that, but they propose some concept and also the term quantum software engineer. So if you are interested, you can refer this proposal. Yeah. And also in 1994, so Susan Stephen, yes, discussion again the challenge of quantum software engineering. So this is the report. This is she discussed the challenge of quantum software in this report, edited by Tony Hall and Robbie Miller, which is a grand challenge in computing held by the British Computer Society, I think. Yeah. So in this report, Susan mentioned that the challenge of quantum software engineering is to revoke and extend the whole of classical software engineering into the quantum domain so that programmer can manipulate quantum programs with the same easy and confidence that they manipulate today's classical program. After that, so there is a quite a long time. So in 2000 20, there are several papers that discuss the quantum software engineering. So the first is by Louis Bobsol. So he presented a position paper called Land of Research Challenge, a landscape of research challenge for quantum software engineering. And also, there is a group of research in the Spain or Portugal, I think. So they held a workshop on the quantum software engineering and quantum programming, and presented the Televilla manifesto for quantum software engineering and programming. And at that time, we published a comprehensive survey on quantum software engineering. So this is a workshop. In this workshop, they present the Televilla manifesto for quantum software and programming. And this is okay. So Luis give a landscape for research challenge for quantum software engineering, which they discuss three aspects: modeling, composition, and verification. Okay, from my understanding, quantum software engineering can be regarded as a layer technology which contains three elements: method, tools, and processes. And quantum software method provide techniques for constructing the quantum software, and tools provide semi-automatic support for this method. And the quantum software processes are the foundation for the quantum software engineering. Actually, the process provides the green glue that holds the method and tools together and enable the reasonable and timely development of quantum software. So here, we'd like to present briefly introduce a genetic view of quantum software engineering, which borrowed the idea from classical software engineering. So QSE is the analysis, design, construct, verification, and management of quantum software. To this end, so the following question must be asked and answered. For example, so what is the problem to be solved by quantum software? And what characteristics of quantum software are used to solve the problems? And how will the quantum software solution be implemented, which include related to the quantum program language and programming system? And the next is what method will be used to detect errors made in the design and construct of quantum software, which means related to this, for example, quantum program analysis, testing, debugging, and verification, and so on. So what will the quantum software be supported in a long period when the user requests corrections, adaptations, and enhancement, which is, I think, is related to the software maintenance and evolution. So actually, from this viewpoint, so QSE can be categorized into three genetic phases. For example, definition, development, and maintenance phases. So the definite phases focus on what? So dealing with the problem that quantum software developers try to determine, and the development phases focus on how. So dealing with the problem that quantum software developers try to describe, and the maintenance phases focus on change. So and the quantum software evolution and something. So based on this, we can propose a very simple quantum software life cycle, borrowed from the idea of classical waterfall life cycle model. For example, for this life cycle, consists 5 parts. The first 5 phases. First is a quantum software requirement analysis phase. So this means to capture detail of each maintenance and to make sure everyone understands the scope. And also, we can have a quantum software design phase to handle the design problem during the design of quantum software. And we also have the quantum software implementation phase, quantum software testing phase, and quantum software maintenance phase. So at the very beginning, the purpose for propose this quantum software lifecycle is that we want to use it as a classification model to categorize the research papers in the quantum software engineering research area. But actually, our life cycle can be regarded as a very simple abstract model, yes, to guide to the. So you can, of course, you can propose some detailed quantum life cycle model, yes, to enhance the quantum software process. So next, I will give a brief brief introduction, current research result in the area of quantum software engineering. So I will from the requirement, design, implementation, testing, and maintenance, which is based on the quantum software lifecycle proposed previous. So here is so in the quantum software requirement area, there is no work actually in the quantum requirement analysis. But now recently there is one paper appeared, yes, to address these issues. But this work is mainly focused on non-functional requirements of quantum software system. And for the quantum software design, there is several work has been proposed for supported design of quantum software. So for example, the quantum software modeling, there is some extensions to UML to model quantum software. And for the quantum software specification, there is an extension with Z specification language for provide some formal specification language for quantum software. And there is also pattern language for identified quantum patterns from quantum algorithms. And also some work has considered the quantum attributes, quality attributes, what kind of quality attribute will be affected by the quantum, for example, computer platforms and something. So for the quantum software implementation, actually is related to the quantum software programming language. So we can say there is a lot of quantum programming language have been developed to support various aspects of to construct, for example, quantum software. So because we focus mainly on quantum software engineering, so we do not talk about the quantum program language. There is a lot of survey papers regarding quantum program language. So this is a pattern language for quantum software. So there is some Python tab, and which is closely related to some quantum features proposed by Frank Lehmann from Germany, and in this paper. And for quantum software testing and maintenance, so there is quite a lot of papers have been published. For example, there is some papers that started assertions in quantum software. Some work that extended the classical Hall logic to the quantum Hall logic. And some work has been considered to support quantum software testing, for example, from the fuzzy testing perspective and property-based testing. And also recently, there is some search-based testing for quantum software. And for the quantum program debugging, there is also quite a lot of paper, yes, to consider this, to try to solve these questions. But since a quantum variable cannot be copied, so quantum program debugging is basically fundamentally different from the classical debugging. So you cannot set some breakpoints to observe the intermediate state of a quantum bit. So this make some challenges for debugging quantum program. And okay, so finally, I would like to discuss some challenge and opportunity in quantum software engineering. So for quantum software design, so I consider there is some research topic that should be considered, just similar to the classical software design. For example, we can, identify some quantum architecture patterns and styles, and also maybe we can develop some quantum architecture description languages, which may be an extension of classical architecture description language to describe, to specify the quantum components. And also, we can consider, for example, to identify some quantum design pattern. Although there is not so many quantum algorithms and quantum applications, but we can maybe, as a first step, we can consider some single design pattern for quantum software. And also, so we should develop some design models which based on some idea from the classical design model, yes, to cover the quantum aspect for quantum software system. So for the quantum software implementation, so because it's related to the quantum program language, but as you know, so there is no high-level quantum program language. So recent high-level program language, I don't think they are a real high-level program language, because they basically operate on the quantum bit when they handle the programming quantum computer, just like assembly language in the classical computing and also machine language. So we should develop a really new high-level quantum program language to support efficiently programming quantum computer. And since quantum algorithm is very different from the classical algorithm, and it is very difficult to develop it. So maybe we can propose some method to automatically generate quantum code on quantum algorithm and something. So for quantum testing, so there is a lot of things I think we can do. For example, how to define testing coverage criteria for quantum software. Although there is one or two paper have been published, but I think there is a lot of space to explore these directions of area, and also how to automatic and efficient generate test cases. For debugging, so there's no efficient debugging method recently for debugging quantum software. And for verification, there is, although there is some method to propose for based on the whole logic and other rational logic and something, and temporal logic. So there is no efficient method there's actually, yes, to support fully verifying the quantum program. So for the software maintenance, we should answer the following question: how to understand the existing quantum software, how to modify the existing quantum software, and how to validate the modified quantum software. So we should develop related techniques and approaches to support this aspect in maintain and evolution of quantum software. So actually, there is some international events start from the 2000, I think. Yes, 2000. Yeah. So, for example, this is the International Workshop of Quantum Software Engineering, which co-located with the ICAC workshop. This is third International Workshop of Quantum Software Engineering, which I'm a PC co-chair. So if you're interested, so you can go to the website to see something. And also, from this year, there is IEEE International Conference of Quantum Software. Will be held in July. I forgot the place and something. Okay, so in this talk, we try to present a comprehensive survey in the field for quantum software engineering. But since there's quite a lot research result, and it's a very broad research area, so I don't think we can do it well. We also discussed some challenges and opportunities in the area of quantum software engineering. And I think it is vital that a complete software engineering discipline emerges for quantum software development. So if you're interested, so you can look at my paper, which is uploaded at arXiv. So in this paper, I summarize, I give a survey in the area of quantum software engineering. So thank you for your listening. I'm sorry for that.